everyone. So my name is Isham Jora from Sintef community in Norway, and I will present the work, or just a quick overview of the different topics that we have tackled in Subtask C, that is titled Tools and Methods to Leverage the Thermal Demand Response Potential in Buildings Connected to Thermal Networks. So of course, it's a collective work with many co-authors and contributors that have helped creating the content and reviewing all the different methods and discussing the different methods that is in the technical report. So again, just a brief overview of the different topics that we have discussed in that Subtask C. So, of course, quick introduction, we have continuous digitalization of the buildings and the thermal networks, and that enables a lot of new data-driven methods to leverage that data for smart management of the district heating and cooling. Let's not forget the cooling and the buildings. And of course, the goal is to make everything more reliable, sustainable, efficient, and to integrate renewable energy sources. So again, in that Subtask C of the Annex 84, we looked at how the different algorithms or methods can leverage that data and which numerical tools are available to model and test smart thermal operation of buildings connected to thermal networks, and how to optimize all of that. So the first part that we look at is, of course, the modeling of the buildings, the building clusters, and the thermal networks. What tools are available for engineers and researchers to model these complex systems and also integrate the demand response for energy flexibility controls and strategies. And there are many numerical tools, but many of the modeling tools that are used by engineering companies or utility companies, they're not necessarily suitable to integrate all of that, to be able to model both the buildings, many buildings, and the thermal network, all of that in a dynamic way, and to integrate complex control strategies. But there are more advanced modeling tools that probably many of you know that can tackle all that, multi-domain modeling tools where you can model both the thermal network and the buildings and implement advanced controls. So for example, Transys or some Modelica libraries, SimVicus, IDICE and IDA districts, DemoSim and CitySim to name a few. Of course, we also see an increasing trend of using machine learning or AI methods to generate black box data-driven models for modeling or representing the dynamic behavior of buildings, clusters of buildings, also the thermal networks. And there is also a rise of co-simulation frameworks or co-simulation platforms. Many use the FMI, FMU standard to communicate or to enable the communication between specific domain models and make them exchange information and have a well-running co-simulation. So for example, you have certain tools and platforms that enables you to connect Energy Plus modeling or simulating the buildings and connect it to Modelica to simulate the thermal network behavior. But there are some restrictions or some challenges in all of that. At the moment, simulating large clusters of buildings connected to thermal grids with advanced smart control for demand response, it's still quite complex. That requires some programming skills, and the learning curve is quite steep at the moment. There is a need for better documentation on doing that. The integration of the different tools and the interoperability of the different tools is not perfect yet. They are, when we've been in touch with the people using those tools, especially a lot of PhDs and postdocs, they reported some bugs, some glitches, some issues, and it's not always simple to navigate all that complexity. And also, it is still quite challenging to scale up the size of those models to be able to simulate with a fairly good detail level, hundreds or thousands of buildings at the same time. So this is still a challenge. Then, of course, the digital twin. So this concept of digital twin, which is a virtual replica of physical assets. So in here, buildings and thermal networks with a two-way communication. So they exchange information to be able to get the information from the real system to continuously recalibrate those models and then run some simulation and optimization. And then that information for optimization is sent back to the real system to optimize the actual operation in real time. So this digital twin concept is popping up everywhere, and also as well in the smart management of thermal networks. It is seen as the key technology to really have this transition towards fourth and fifth generation of district heating and cooling, low XGRG systems that are able to include the forecast of the weather, of the energy production, of the different energy prices, and optimize the use of decentralized energy storage, energy production, and demand response assets. And also to make the coupling with the electricity and gas grids or other energy grids. And of course, at the core of digital twins, we have a model that models the different assets, so related to the previous slides. And again, there is some work to be done to make sure that we can actually develop accurate models, multi-domain numerical models that enable as well either multi-domain numerical models or co-simulation frameworks that work well and are easy to develop, expand, and maintain. And of course, on top of that, you have an increasing use of machine learning and AI methods to run all types of data-driven predictive control or adaptive control and optimize the efficiency of the whole system and the cost of operation. Then, with this digitalization of the different systems, there is, the continuous deployment of smart heat meters. There is tons and tons of data, so constant flow of data with a fairly, a new level of time resolution. So there's a lot of information from thousands and thousands of buildings. That's very nice to have this continuous monitoring of in here heat demand of the buildings that are connected to the district heating, and the same for district cooling. And having that information, that dynamic information of how the profile of the demand is for the different buildings, that's very important to understand better the behavior of the customers, how it changes with time and with the seasons. That helps to forecast the demand, to help maintaining or renovating the different building stock or the network itself, and of course to design proper smart demand response and demand management. But also with all that information that helps to detect faults in the buildings themselves or in the thermal networks. But at the moment, those smart heat meters, they've been designed for building purposes. So the data, the time series that they produce is restricted in terms of, reliability and especially the time and measurement resolution. So you have hourly value with truncated or rounded values of the heat demand. And sometimes you have some large data gaps. And also you typically have only the main meter data, you don't have submetering. So that poses some limitation on how this data can be used for certain application. And researchers have been working on developing new algorithms to try to, tackle those challenges linked to this low data resolution, to impute missing data and to disaggregate heating and domestic hot water production from the total heat demand recordings. So of course we're talking about implementing a smart control and demand response in thermal networks. But for that, if we want it to be successful, it's important to have systems that work as designed or as expected. So it means that the faults are not there, and unfortunately they are. The prevalence of faults in district heating systems and in buildings and heating systems of buildings is quite large. At least the different exploration campaign have found that most buildings, they have some faults or under optimized settings. And that's why we see the rise of fault detection and diagnosis as well for district heating systems. And of course, this is enabled by the fact that now we have more and more data, continuous time series of the operation of thousands of buildings, and we can try to see some correlation that are linked to certain faults or typical underperformance. So recently there have been, there is continuously some computer-assisted or automated fault detection and diagnosis methods that are, developed at the moment specifically for thermal networks and substations of the thermal networks that are in the buildings, and also a bit beyond the substation, what's going on in the heating systems on the building side. Of course, the goal or the aim of those automated fault detection or computer-assisted fault detection is to reduce the time between the fault occurring and when we detect it, so therefore decrease the repair time, and also enable predictive maintenance to tackle the faults, to fix them before they lead to problematic issues. At the moment, most of those methods, they are rule-based or based on some known KPIs or specific KPIs with alarms that are triggered by threshold that are made or set by a specialist. And it's a lot as well of anomaly detection methods or comparison between a numerical model that is supposed to be the ground truth of fault-free systems and the real systems. So because it runs, we need data for testing and developing and training those different methods. And we've seen that there is some limitation of the data, and there is also limitation, therefore, on those fault detection and diagnosis. So at the moment, there is very little high-quality data with ground truth or information on the faults in district heating systems. That limits a lot our capacity to develop new methods and to test and benchmark the new methods. So we really have to put some more emphasis on creating those new data sets and having them open access. As mentioned before, the resolution and time resolution of the smart heat meters is a bit limited, and that does not enable to detect certain small or sudden events which are linked to a certain fault. So again, the smart heat meter data at the moment is a bit is just at the limit of being useful for certain faults. So again, we need to put more effort in collecting, curating, and structuring quality data to have an open access, and if possible, to structure this data and label it and add meta information that should follow some taxonomies that are accepted and discussed and useful. So we should make a better use of taxonomies of faults. And we encourage the different companies to collect this data in a structured way, and of course to make it available to everyone if possible. Then all of that, so we're talking about a lot of data, a lot of implementation of new models. The problem is usually the scalability of that. How is it that we deploy new methods from one case study to several case studies in a, let's say, a fast and efficient way without spending too much time or just making mistakes? So really the scalability and interoperability of the different solution is really key to that, and probably the best method for that, or the best approach for that, is to make the best use of semantic principles and ontologies. Those are frameworks that are like machine readable representation of all the data and the information about the different systems, so that we can link all this information And there are a number of different ontologies specifically for buildings and also for automation systems, and we should be better at making use of it. And for demand response and energy flexibility, recently there's been also some development in terms of ontology. So, for example, the eFont ontology that has been specifically designed or created to tackle the different assessment methods of demand response and energy flexibility. So, basically, linking all the information needed to calculate demand response KPIs, and that can also be linked to the other well-known ontologies like SAREF and BRIC. And there's more and more demonstration projects and studies that show that in terms of scalability and implementation, if you make good use of ontologies and BIM information, then you really cut the implementation time of those smart control applications. So just key conclusions or a takeaway from our activity. So again, the digital twin is really like at the heart of all the new projects of smart buildings and buildings performing demand response in thermal networks. But of course, again, at the core of that, there is a need for more accurate dynamic numerical tools that can handle both or at the same time detailed dynamic modeling simulation of the buildings, of many buildings, the thermal networks, and enable the implementation of smart control, and also can handle optimization subroutines and interaction with external signals, forecast of the weather and incentive signals from the grids. The data from the smart heat meters is very valuable, but we would love to have a bit higher resolution in terms of time resolution and measurement resolution that will really trigger or unlock a lot of new possibilities. And also, if there is more implementation of submeters in buildings, and especially large buildings, that would be fantastic. Again, to try to tackle those issues, many new algorithms to try to mitigate those limitations, to impute the missing data, to smooth the data, to disaggregate the data. So fantastic work made by the community to make open access and open libraries for example, Python tools or R tools. And there is also continuous effort in developing new automated fault detection and diagnosis, and also trying to curate those open data set so that the whole community can take it and use it to test and develop their own solutions. And lastly, again, we should focus on making the best use of ontologies and semantic principles to implement and deploy all of those smart applications in buildings and thermal networks. So that's it for me. Thank you very much for your attention. And of course, thank you to the many contributors and the people who have helped us, reviewing, discussing, diving into all of those different methods and to write the deliverable.